Hey everyone, today we're pleased to be here with you with a tutorial about outliers detection with a statistical method. To begin with, what is first an outlier? An outlier is data that deviates significantly from the rest of the other data, as if it were generated by a different mechanism. We may refer to data objects that are not outliers as normal or expected data. Similarly, we may refer to outliers as abnormal data. In figure 12.1, most objects follow roughly Gaussian distribution. However, the objects in region R are significantly different. As you can see, it is unlikely that they follow the same distribution as the objects in the dataset. Thus, the objects in R are outliers in the dataset. Now that we have a better understanding about what an outlier is, let's explain the different types that exist. In order to be better at identifying them, we have three different types: global, contextual, and collective. Global outliers are the easiest ones, since they are globally as their name says. They deviate from the rest of the whole dataset. A perfect example will be again the figure 12.1 that we already shown. That from the whole data, the 2 points in R are our global outliers. On the other hand, contextual outliers depends on the context. As all the outliers, they deviate significantly, but here in a specific context. For example, temperature is 8 degrees. Is that an outlier? I don't know. But if we say that that is in Yucatan, then it definitely will be, since we're always melting in here. Lastly, collective outliers, in the simplest world, will be like a global outlier, but instead, they act like a subgroup of the whole dataset, with its own mechanisms, but they individually may not be considered outliers. An example will be the figure 12.2, where the black points together are outliers, but each one of them, compared to the rest of the data, may not be an outlier. We are no experts in the outlier department, but to get our diplomas, we may need some tools to be actually able to identify them, don't you think? And today we're going to concentrate in the statistical methods. And what are they? The general idea behind the statistical methods for outlier detection is to learn a generative model fitting the given dataset, and then identify those objects in low probability regions of the model as outliers. An example will be taking figure 12.1 again. The data follows a Gaussian distribution for the points in the R region. We could try to fit the Gaussian distribution, but since it is very low, it is unlikely that those data were generated by the Gaussian model, thus they are outliers. However, there are many ways to learn generative models. In general, statistical methods for outlier detection can be divided into two major categories: parametric methods and non-parametric methods, according to how the models are specified and learned. So that we can have our PhD in outliers, we need to understand those two categories. A parametric method assumes that the normal data objects are generated by a parametric distribution with a parameter negative. The probability density function of the parametric distribution fx negative gives the probability that object x is generated by the distribution. The smaller this value is, the more likely x is an outlier. A non-parametric method does not assume in a priori a statistical model. Instead, a non-parametric method tries to determine the model from the input data. Note that most parametric methods do not assume that the model is completely parameter-free. Such as an assumption will make learning the model from data almost mission impossible. Instead, non-parametric methods often take the position that the number and nature of the parameters are flexible and not fixed in advance. Examples of non-parametric methods include histogram and kernel density estimation.
The algorithm. The method that today we'll be approaching will be parametric, specifically for univariate outliers based on normal distribution. But what is univariate data? Data involving only one attribute or variable are called univariate data. For simplicity, we often choose to assume that data is generated from a normal distribution. We can then learn the parameters of the normal distribution from the input data and identify the points with low probability as outliers. Let's start with univariate data. We will try to detect outliers by assuming the data follows a normal distribution. In this case, we will practice with the simplest form to detect outliers, which is using maximum likelihood. Using the mean and the standard deviation, we can find outliers in a set of values. We will assume that the average of the data follows a normal distribution, which is determined by two parameters. The mean, which is equal to the sign mu, and the standard deviation, which is equal to the sign sigma. We can then use the maximum likelihood method to estimate the parameters mu and sigma. That is, we maximize the log likelihood function. Here's the formula for the maximum likelihood methods to estimate the parameters mu and sigma. Now, taking derivatives with respect to mu and sigma and solving the resulting system of first order conditions leads to the following maximum likelihood estimates, which we can see. Here we can see the two formulas corresponding to mu and sigma, which are related to the maximum likelihood method. After that, we have to take into account the following rule that says that the region between 3 times the standard deviation from the left and from the right of the mean contains the 99.7% of all the data in our distribution. That means that we can assume that any data that is outside that range can be considered as an outlier. If we see this rule in detail, a standard deviation from the mean on the right plus a standard deviation from the mean on the left should contain 68 of our data. Similarly, if instead of one mean deviation you use 2 standard deviations, you should include 95 of your data. And if you use 3 standard deviations, you should contain 99.7 of the total values. This means that any value that you grab out of those 3 standard deviations must be within the 0.3 of remaining data, which can be considered as outlier. This was only to clarify the concept of that 68, 95, 99.7 rule. Now, let's see the applications of outlier detection with maximum likelihood. Okay, first we have to import these 4 libraries here. Each of one of them is used for a specific function. The first one is used to graphic things. The second one is the source of our dataset. The third one is used to work with data frames, and the fourth one is used to make mathematical operations. In this case, what we are going to do is load a data frame from sklearn. The most popular one is the iris dataset. What we are going to do is take 2 variables, one that we already know that has an outlier and other that does not. So in this part, you can see here that we are loading the dataset from the sklearn library. Then we define a function called flowers. In this case, this returns a value called flower that belongs to the target names. In this part of the code, we are dividing the dataset in different parts. Like in this one, we are taking only the features of the entire data set and not taking all of it into one variable called iris data. In this case, iris data, it's only storing the features of the entire data set. And we can see here the given features: sepal length, sepal width, sepal length, petal width, and the species. Now, we are going to choose the sepal width and the sepal length variables and their values to apply the outlier detection with maximum likelihood. In this part of the code, we are creating two new variables. One is called sepal width and the second one is called sepal length. They both do almost the same thing, but with different columns inside the data frame. In this case, we are taking the data from the iris data, but we are taking two different columns, sepal width and sepal length. In both cases, we are extracting only the values inside that column and keeping them in a kind of list that is displayed here. First is displayed sepal width with all these values, values, and sepal length with all these variables. This is only done so we can see the values inside those columns. Now, let's assume that the average temperature follows a normal distribution, which is determined by two parameters: the mean, which is mu, and the standard deviation, sigma, where n is the total number of samples. Taking derivatives with respect to mu and sigma and solving the resulting system of first order condition leads to the maximum likelihood, mean, and the standard deviation. Okay. In this part of the code, we are getting the mean of the sepal width, the variance of the sepal width, and the standard deviation of the sepal width, and then displaying the results in screen so we can see what each value is equal to. Now, we are doing exactly the same that we did with the sepal width, but now we are doing it with the length. We are taking the mean, the variance, and the standard deviation and displaying it in screen so we can see what each variable is equal to. The mean and the standard deviation are now calculated. The next step is to seek for the existence of outliers. What we're going to do is apply the rule of 68, 95, 99.7 that says to follow a normal distribution, the 99.7 of the data is supposed to remain within the rule, which is mu plus minus 3 times sigma. We have described this rule previously in the video, so we are going to create a formula or a function that represents this inside our code. We can see here that the outliers function gives or receives three different arguments: data, data mean, and data standard deviation. Okay, so to follow these rules, we have to get the maximum right, which is mu plus 3 times sigma, and that's equal to this part of the code, and the maximum left, which is the same but with minus 3 times sigma. And then we are going to use a list comprehension or a comprehension list to get only the values that are outside the maximum right or the maximum left, and then our function is going to return those values. Now we try the function outliers for both of our variables. In the case of sepal width, we detected an outlier which is equal to 4.4. That means that sepal width had one outlier according to the outlier detection with maximum likelihood. In the case of sepal length, we didn't recognize any outliers. So that's all for all. Subscribe, like, and share with your friends so we can keep doing this work.